Alright, hello everybody. Today I'm going to do two things. I'm going to be making two videos today. The first is going to be to finish the first handout from section 1.5, talking about transformations of functions and just talking about the vertical transformations separately from the horizontal transformations. In my second video that I'll be making today, we will be combining those transformations together and be basically performing both vertical and horizontal transformations simultaneously. So the first thing I want to point out is that yesterday we covered vertical transformations on Tuesday, and vertical transformations are also what are called outside transformations. So we graphed three transformations of a given function f of x whose graph is below, and I want you to notice that all of the changes are occurring outside of the function notation. So for part A, g of x was defined by taking all the outputs of f of x and subtracting 2 for the same x values. That resulted in a shift. I want to point out to everybody that sometimes my video, the recording posits on its own. So let me just re-summarize. When we graphed g of x in part A, subtracting 2 is a shift down by 2 units. In part B, h of x was obtained by multiplying all the function values of f by 2. That's a vertical stretch away from the x-axis by a factor of 2. And then in part C, r of x was defined by first multiplying all the outputs of f by 2, right here. Okay, and then subtracting 1 from those values. So we always do stretching or compressing before we do any shifting. So for part C, that was taking the graph of f, doing a vertical stretch by a factor of 2, and then that is followed by a vertical shift down 2 units. Okay, and we graphed all three of those yesterday, and I made a table. We found all the x coordinates stayed the same. The only thing that changes with vertical transformations is the y coordinate. So we saw the effects on the original graph by performing those operations, or those transformations more specifically. Okay, and then what we did, on the top of the next page I summarized the transformations in general. So given a function f of x, okay, for real numbers c and d, okay, up here at the top, you have to make sure that your scaling factor c is non-zero. I can create a new function or new expression by first multiplying f of x by c, that'd be the scaling factor, and then adding a real number d, and that would be your vertical shifting factor. Now, number 1, it says first you vertically scale by a factor of absolute value of c, which means essentially what you're doing is you're multiplying all the outputs or y coordinates by absolute value of c. The reason we're putting in absolute values is because if c ended up being negative, right, number 2 says reflect or follow that scaling with a reflection over the x-axis. Now again, if c in absolute value is greater than 1, the scaling is a vertical stretch away from the x-axis, and if the absolute value of c is between 0 and 1, say like 1/2, the scaling is a compression towards the x-axis. And then finally, number 3 says, then you would shift absolute value of d units up when d is positive, and absolute value of d units down when d is negative or less than 0. And ultimately what you're doing to all the points on the graph is you're adding capital D to all the y coordinates. Now, if you look at this note on the bottom, if you look at this note on the bottom, okay, if you factor out that scaling factor c, okay, and have f of x plus what's left over, d in parentheses, you would do the steps backwards. So you'd first do your shifting up or down by absolute value of d units, and then you would do your reflecting and your scaling. So C would be your vertical scaling factor. Okay, and then what we did was, from here, we finished up class by starting with algebraic expressions. So taking the graph of, say, in part A, f of x equals 2x plus 2, and we wanted to find the function g of x, whose graph is the same as the graph of f of x after it's been compressed vertically by a factor of a half and shifted down 3 units. I think we ended up getting g of x equals x minus 2. Okay. And again, if you were there in class, we saw how to work that out. And then in part B, we started with the graph of h of x equals 2x squared plus 4, and we wanted to find the algebraic form of the function g of x, whose graph is the same as the graph of h of x, and we stretched vertically by a factor of 2, and then we shifted up 5 units. Okay, and I think what we got is the new function g of x would be, it was negative 4x squared, and then I think we got a minus 3. Okay, because we multiplied this by negative 2 first, okay, to get negative 2x squared minus 8, and then the shifting up 5 units was just adding 5 to that. So that's how I obtained minus 4x squared minus 3. Now what I'm going to cover now is horizontal transformations, which are also called inside. Okay, we call them inside changes, and you'll see why in just a second. Now I'm going to start doing this again from scratch, okay, like we did for vertical transformation. So again, now I have 3 new functions defined in terms of the original function. So on your handout you should have 3 copies of the graph of f, and we're going to graph these 3 transformations of f: g of x, h of x, and r of x. Okay, so we'll take care of part A first. Okay, so it says use the graph of the function y equals f of x below to graph g of x equals f of x. I'm sorry, I'm just changing the size of my... There we go. Okay, so first what I'm going to do is work on part A. And it says g of x is f of x minus 2. Okay. Now, with horizontal transformations, or what I'm calling inside transformations, which can be seen if you look in here, right? It's not just f of x anymore. Now I have changed the inside, hence why it's called an inside transformation. And I've done this by subtracting 2 from x. Now, you hopefully noticed that with vertical transformations, the only thing that changed was the y-coordinates, or the range. With vertical transformations, the domain does not change. Now, with horizontal transformations, strictly speaking, this time the range is not going to change, so the y-coordinates are going to stay the same or fixed. This time the x-coordinates are going to change, and you'd be tempted to say, if you look over here, you'd be tempted to say that since I'm doing x minus 2, I'm subtracting 2 from all the x-coordinates in my domain. And this is where this gets slightly, I guess, strange. It actually turns out, to be able to plug anything into G, you actually have to add 2 to all the x-coordinates to be able to plug something in on the right-hand side. So what the textbook does, or what we're going to do, is I'm going to let x star equal x minus 2. Okay, and x star is in the domain of f, and x, right, you can see it up here, x is in the domain of G. Okay. And what you'll see is, so x is in the domain of g. So what I'm going to do here is you look, x star is in the domain of f, and it's set equal to x minus 2. And if you solve for x, you're going to get x is equal to x star plus 2. So, right, how do I get all the things in the domain of g? So this is a value, this is a input of g, right? It's a value in the domain of g. Remember, x star is an input of f. Okay, so if I want to find my domain of g, what I have to do is take all the inputs or values in the domain of f and add 2. So this is where things are kind of opposite, right? All the operations are opposite. If you look inside the parentheses where I have f of x minus 2 up here on the top, right, if I'm looking at this right here, okay, when you see x minus 2, you're really adding 2 to all the x coordinates to get your new x values for g. The y coordinates are going to stay the same. So I'm going to go ahead and make a table. And I've got to make some room here. Just pause the video for a second. So this time I have to make 2 different tables. I can't just add to the tables like I did in the first part. So I have x f of x and I have x g of x. Okay. Now, looking at the graph, you'll see that you had those 4 points for f. They're the same as yesterday. All those sharp points had x coordinates -2, 0, 2, and 4. And the corresponding outputs of those x values are -2, 2, 1, and 1. Okay. And actually, before I make this table on the right, let me actually do one of these. So what happens when I do, well, actually, hold on. So first of all, right, I just solved for all the new inputs of g, so I had to add 2. So now the inputs become 0, 2, 4, and 6. Okay. And I'll just do this next one on the bottom. So what if I try and do g of 0? Well, remember how f is defined. G is defined, sorry. G of 0 is defined to be f of 0 minus 2. Okay, that would be f of -2, which looking at the table or the graph would give you an output of -2. So there's the first one. Okay, I'll do one more before you start realizing. Notice that the output of g at 0 is the output of g, the output of g at 0, okay, is the same as the output of f at -2. Now I can do the next one. Alright, what's g of 2? G of 2 is f of 2 minus 2, which would be f of 0, which ended up being +2 if I look at the table on the left. Okay, so notice again, when I define g as f of x minus 2, I'm really adding 2 to all the x coordinates, but nothing happens to the y coordinates. Okay, and now I can plot those points. Let me go back to a green color. So I have now 0, minus 2, this point right here. I have 2 to the right and up 2, that point right there. And then when x is 4, g of x is 1, right here. And then I don't have room for it, but let's say 6 is right here. Okay, now g of 6 is +1. Okay. And what you'll notice has happened is that the graph is shifted to the right 2 units. Okay. So for g of x, this is a shift right 2 units. Okay, so actually whatever's being subtracted from x, that number is positive. So I'm subtracting +2, so I'm shifting right 2 units. Okay. Okay, so now we can go ahead and start working on part B. So h of x is defined, the values of h are defined by f of 2x. Okay. Now again, when we do this, h of x is f of 2x, and we will, again, this input of 2x, we'll call that x star. Okay, so x star is an input of f, and okay, x is the input of h. So now that x star is 2x, solving for x will give you x star over 2. Okay, so what this means is to be able to plug an x value into h has to be anything in the domain of f divided by 2. And I'll make that table again for f. The inputs were -2, 0, 2, and 4. And the outputs were -2, 2, 1, and 1. And when I make the table for h, I have to divide all the inputs by 2, which would give me -1, 0, 1, and 2. And you would again see that all the outputs are going to stay the same. Okay, so I'll go ahead and plot those. So when x is -1, I get -2. When x is 0, I get 2. So what you're going to notice is that point in particular, you're either stretching or compressing towards or away from or towards the y-axis. So if you're already on the y-axis when you do a scaling, those points don't move anywhere. Now when x is 1, you get this point. So when x is 1, h is 1. And when x is 2, h is 2. And we can connect all those with line segments. And there's the graph of h. Okay. So interestingly, when you look at, if you look back at part B, when you're doing on the inside of the parentheses, when you're actually multiplying by 2, you're actually multiplying all the x coordinates by the reciprocal 1/2, and that causes a compression. So the graph of h is a compression towards the y-axis, but this time it's by a factor of the reciprocal, which is 1/2. So it's a compression by 1/2, and you'll notice all the y coordinates are the same, but we multiplied all the x coordinates by 1/2. Now lastly, we're going to graph r of x, which is defined as f of 2 times x minus 2. Okay, so r of x is f of 2 times x minus 2. Again, these are inside changes because all the factors and scaling are done inside the parentheses. And I will again, this 2 times x minus 2 is going to be x star, so this is an input of f. So x star represents all the things in the domain of f, and x is an input of r. And what we'll do is x star again is set equal to 2 times x minus 2. And then solving for x, you would first divide by 2. So x minus 2 is going to be x star divided by 2. And then finally, solving for x is going to give you x star over 2. So you first divide everything in the domain of f by 2. And then you would add 2 to all the x coordinates after that. So divide all the x coordinates of f by 2, and then add 2. Those will give you all the new inputs for r, and all the y coordinates again are going to stay the same. So now, again, I have my two tables, x and f of x, and I had -2, 0, 2, and 4 with outputs negative 2, 2, 1, and 1. And then now when I make my table for R, okay, first you divide all the x coordinates by 2, and then you add 2. So for the first one, if I divide the x coordinate of negative 2 by 2, I get negative 1, and if I add 2, I get positive 1. If I divide 0 by 2 and add 2, I get positive 2. If I divide 2 by 2, I get 1, and I add 2, and I get 3. And if I divide 4 by 2, I get 2, and if I add 2 to that, I get 4. And again, you would see that all the outputs would stay the same if I actually worked it out algebraically. And then I will use that table and plot all the points. So when x is 1, I get negative 2. When x is 2, I get positive 2. When x is 3, I get 1. And when x is 4, I get 1. So there would be the graph of R. Okay, now what you'll see is, if you look back at part C, right, that multiplication on the inside by 2 is really, oh, I lost my graph. Oh, shoot. Well, let me see if I remember what it was. Negative 2, x is 2, I got 2, 1, 1. Sorry, R got deleted somehow. So there was the graph of R. So the multiplication up there that I've circled by 2 is really compressing u by a half. So you'll see that the new graph is kind of a squished version of f, or a compressed version of f. And then the x minus 2 is shifting that result 2 units to the right. So all the operations are opposite. Okay, when you see a multiplication by 2 up here, it's really multiply all the x coordinates by a half, so you're doing the reciprocal, or instead of multiplying by 2, you're dividing by 2. And then the x minus 2 up here is you're really adding 2 to all the x coordinates. So this function is a compression, a horizontal compression by a factor of 1/2, followed by a shift right 2 units. Okay. So now we'll do some algebraic examples, and then in my second video we will combine all transformations together. Okay, and I'll show you how to kind of do everything shorthand instead of doing everything from scratch like we've been doing. Okay. Now, here's the summary of transformations. So again, for real numbers a and b, again, you want to make sure that a is non-zero. The graph of y equals f of a times x minus b is the graph of x. Now, first, you're going to scale horizontally by a factor of 1 over the absolute value of a. So right again, up here you see a multiplication by a, but really what you're doing is multiplying all the x coordinates by 1 over a, or, well, the absolute value is getting rid of the negative. Now you would see that if a is between 0 and 1, like 1/2, it actually becomes an expansion away from the y-axis by the reciprocal of a. And when a is greater than 1, like in examples b and c above, remember a was 2, the horizontal scaling ended up being a compression. If a is negative, you would follow that scaling by a reflection over the y-axis, so you'd multiply all x coordinates by -1. And finally, okay, notice if you look up here, oops, b is what you're subtracting from x, and when that value is positive, like x minus 2 for instance, you'd actually be shifting to the right by absolute value of b units, and you'll shift absolute value of b units to the left if b is less than 0. In either case, you're adding b to all the x coordinates. Okay. And again, This time, if you were to say distributing that a value through, okay, so if it was f of ax plus b, okay, so if you don't have that extra set of parentheses inside the outer parentheses, you reverse the steps and do them backwards. Okay. Alright, so let's see an example of doing this algebraically now. So same functions that I was dealing with the horizontal transformation. So again, if the original function is f of 2x plus 2, we're going to compress horizontally by a factor of 1/2 and shift 3 units to the right. Okay, so the compression by a factor of 1/2, this is actually going to tell me that a is actually the reciprocal, positive 2. And if I'm shifting b 3 units to the right, that means b is positive 3. So now the new function g of x, okay, I'm just going to write the general formula, or general form of horizontal transformations. I get f of a times x minus b. And first thing I'll do is replace a with positive 2, and I'll replace b with 3. So again, that's telling me to do a horizontal compression by 1/2. B is positive 3, that's a shift right 3 units. Okay. Now in the next step, what you're going to do is I'm going to take this, well, one thing you can do first, if it makes it easier for you, you can go ahead and distribute the 2. So inside the parentheses I would end up with 2x minus 6. Now, this guy is now my input, and what I'm supposed to do with that, f tells me to multiply that input by 2 and add 2 to it. So this whole value is going to go in place of x in the original expression. So this would be 2 times the input of 2x minus 6, and then I would add 2. And then when I simplify that, you're going to get, well, you distribute through, you're going to get 4x. If I distribute that 2 to the negative 6, I'm going to get minus 12, but then I'm going to be adding 2. Minus 12 plus 2 is minus 10. Okay, so there is the algebraic form of the function g, obtained from the graph of f by compressing horizontally by a factor of 1/2 and shifting 3 units to the right. And again, what I want you to notice is the original function was linear with slope 2 and y-intercept 2. And after applying those transformations, you still end up with a linear function, but the slope is now 4 and the y-intercept became negative 10. Okay. Okay, so now for part B. Alright, so this time we're going to find the algebraic form of a function g of x, whose graph is the graph of h of x. Okay, now first it's going to be stretched vertically by a factor of 2, reflected over the y-axis, and shifted 5 units left. Now, if I stretch vertically by a factor of 2, a essentially has to be the reciprocal of the scaling factor. And by the way, there's a typo here, vertically. That should actually say horizontally. Okay. So that's a typo. This should say horizontally. Okay. But if you look at the second step now, it says also reflected over the y-axis, meaning a should be negative. And the shift left 5 units is telling me that b should be negative 5. Okay. You make some room. Okay, so now g of x is going to be a transformation of h and inside the parentheses you'll have a times x minus b. Okay, so leave h alone for now. A we now know is negative 1/2, and then I have x minus negative 5. Okay, and I'll simplify that. That'll be h of minus 1/2. But notice what happens to the sign. Right, if you're shifting left 5 units, you're actually going to see an x plus 5 there. Okay, so this is a horizontal stretch by a factor of 2, so a is 1/2. The reflection over the y-axis tells me furthermore that a is negative, and a shift left 5 units is x minus negative 5, which becomes x, what you see is actually an x plus 5. Now, come back up here to the expression for h, and I'm going to take, again, how this works. It's just like function composition. This is why we talked about composition before transformations. This whole negative 1/2 times x plus 5 is going to replace that x in the expression for h. So this is going to be 2 times my minus 1/2 times x plus 5 squared, and then we have a plus 4 on the outside, right? So this replaced my value of x in the expression for h. Now in my next step, I'm actually going to, I'm not going to distribute this minus 1/2, but what I am going to do is I'm going to distribute the power to the product. Okay, so I'm going to leave the 2 out front, and then if I square negative 1/2, I get 1/4, and then I'm going to have x plus 5 squared. So I squared the negative 1/2 and I squared the x plus 5, and I still have the plus 4 on the outside. And then the last thing I'm going to do, and you'll see why I'm going to leave it in this form when we talk about quadratic functions. The only thing now that I have to do is multiply 2 and 1/4 to get 1/2. I still have x plus 5 squared, and then I have plus 4. That is my algebraic expression for g of x. So this is what's called vertex form or transformation form, and we're going to talk about that when we get to quadratic functions. You could square the x plus 5 and distribute the 1/2 and expand and combine like terms. That would be called putting it into standard form. Again, we'll talk about that terminology in a later section when we talk about quadratics. But I do want you to notice that the original function h was quadratic, and any transformation applied to a quadratic function is going to again leave you with a quadratic function. Okay. So that completes this part of the video. I will post a video for, I'm going to run upstairs to my office hour right now, grade some papers, and then at noon or 12 p.m. I am going to make a video for the second part of the handout where we combine horizontal and vertical transformations together. Thanks for watching. Make sure you do a lot of practice on this section, especially with the horizontal transformations, just because everything is backwards, right? When you multiply, you divide. When you add, you subtract, and vice versa. Okay, so make sure you spend the extra time looking at that. Thanks, everybody.